Yes, I would like to really thank the local organizing committee, especially Rakesh, for giving me a chance to speak here. So I had given some title which I have written here, but then as Rakesh has also asked me to start, spend at least half an hour to 40 minutes on giving a broad overview of the subject. So if you don't know what these words mean, absolutely don't worry. We will try to, at least by the end of the talk, understand what some of these words stand for. And in some sense, this is a continuation of Indu's talk. Maybe it's actually like could have been before Indu's talk. It's more primitive than what Indu spoke about. Let me first start with a very basic problem that we want to understand, which is a problem in scattering theory. So I'm assuming that students would have seen scattering theory in quantum mechanics, non-relativistic quantum mechanics. So, for example, if you look at Coulomb potential, and you compute scattering, and you may not have seen it this way, but if you have done the quantum mechanics perturbation theory computation, what I draw here, you will immediately be able to relate to it. So suppose, for example, you have some heavy charge center with some charge Q, and some particle, very light particle, is scattering through the potential induced by this. So the potential induced by this center is Q by R, and a particle comes with some momenta Pi, and we are in non-relativistic quantum mechanics. So this is just our three vector, and then it scatters into PF. And we can ask what is the transition amplitude for Pi going to PF when it is scattering in the background of a potential of a charge Q. So maybe advantageous if the students can come a little forward. Can you guys see, by the way, or is it? Otherwise, Alok has to increase his font. Okay, yeah. Yeah, maybe you can come forward. Yeah. That will help. Yeah. Okay. Oh, okay. We can do half of. One. Yeah, my writing is so bad that he couldn't distinguish between the dirt and what I have written. So please stop me anytime if something is not clear. Yes. It's what? Infrared safe. It is not infrared safe. As it gets smaller and smaller, it becomes ultraviolet. So this is something that this problem you would have studied in, I think, in quantum mechanics, that you want to compute probability amplitude for a particle with initial momentum Pi to go to PF. And typically we can draw it like this because we have a Coulombic interaction. I can draw it simply as some kind of a line. And if you draw it like this, then you can check that this probability. So I'm assuming that at least you have seen this notation of scattering operator in quantum mechanics. By the way, please stop me at any time, okay? Because I have no goals to reach, so I can stop whenever my time is up. And it turns out that if you look at it, in perturbation theory, we always start expanding in the coupling, and this the first term we find when we do this is simply given by the fine structure constant. So alpha square divided by mod PF minus PI square. So this is just a transition amplitude for a particle with momentum Pi to go to PF to leading order in our perturbative expansion. But it turns out that if you go to one order higher, which you may or may not have done, then this diagram actually, this is a diagram which is like first order, and you can draw the similar type of diagram at next order. Alpha, thank you, alpha is B square, yes. It looks like this. So this is the second term that you add, and this term goes as alpha square, and this term actually looks like. But there is a problem, because when you compute this term, you see that when you start calculating such terms, you have to do some integration over momenta, and you immediately see that you get integrals like this. Something like this, where the lower limit means the integral is only having evaluated at lower limit. So such integrals are of course divergent, and so actually if you do this calculation, then you get infinity here. So this is what comes here. You get infinity here. So usually you have to regulate it. So you say that I'm going to put some epsilon. And if you do it in detail, what you find is divided by mod pi. And if you continue with this calculation, then it turns out that finally, of course, to go to next order is harder. But if you continue the calculation, you see a really beautiful structure emerge, which is also very brutal, which is that this thing looks like so these dot are terms which are not, we have no infinities, they are finite, but all the finite terms are, they become harder to compute, but every order you always get this term, then its square, etc. So in the end this structure kind of exponentiates, you get like this structure out. And this structure is problematic because, as you can see, if you take epsilon to 0, which is what you should do, then this is a very rapidly oscillating phase. And it tells you that usually in physics where we have some e to the I infinity, then we take it to 0, because if you integrate this against any function, it gives you 0, right? You may have seen this type of identity before. For example, if you look at integral cosine omega x fx, and you take omega to infinity, then we take this to be 0, because cosine, if its omega is very fast, then it's like this, and so no contribution comes from every cycle. So this problem is called infra-red problem of S matrix, problem of scattering theory. So we already see this in Coulomb potential. So if you have not seen it in your course, it's because many books cheat, in the sense that because of this problem, they don't quite look at Coulomb potential. You will typically work with potentials like Q by R square, which actually don't have this problem. So it's really only the Q by R which has this problem, and that's this that is the structure. And so it looks like the transition amplitude is ill-defined. It is becoming 0 actually. And so what is the resolution to this? First of all, that means we have done something wrong, because why should we know that the total probability should be 1, right? But if all probabilities are 0, then total probability cannot be 1. So that means we are doing something wrong in this calculation. Is this clear what I'm saying? That for any pi and pf, this would be 0. But then how can total probability be 1, right? It will not, in the sense that if I would expect that if I did some integral dq pf s pi, then this would basically be summing over all possible probabilities, right? And this should add up to 1. But it can't possibly happen if every term is 0, right? So this was a problem that was realized by Dollard in 71. And he said that, well, we have made a mistake. And the mistake simply is that when we do scattering theory like this, whenever we study in quantum mechanics scattering theory, we always assume that the states in the far past and far future are free particles. So you have some particle coming in which is free, and because naively you would think that this particle is far away from the center, so it came in, so it's free at very early time. It became it was also free at very late time. And okay, then that's a very important input when you derive this kind of S matrix element, right? Because these are supposed to be, so this is supposed to be the state in the far past, state at t equal to minus infinity, for example. And what Dollard realizes that it's actually not true for Coulomb potential, and it is not true in the sense that if I even look at classically, it's not even true actually in classical theory. So classically, if you look at the trajectory of a particle in Coulomb potential, and you ask what is the trajectory at very early or very late time, I mean, this is we just have to solve this equation. Equal to where x0 is the point at which your big charge is sitting. I'm taking the charge of this particle to be unit 1. Otherwise, you'll have q times some small q, etc. So classically, the trajectory also turns out to be what you would naively expect as t goes to plus or minus infinity, plus some term which is proportional to this velocity times. So you see that even if you go to very, because at t plus or minus infinity, log doesn't go down, right? Log of infinity is infinity. So even if you go to very early or very late time, your trajectory is never the trajectory of a free particle. So that means that we should not evaluate the S matrix in the states, eigenstates of a free particle, but we should look at states which capture this specific form of the asymptotic trajectory. And then, so that basically was what Dollard said, and his answer was very, very simple. He took this, did some more detailed analysis, and found that the correct asymptotic states are as follows. So for example, as at initial time, as t goes to minus as t goes to minus infinity, the state, which we can write it now as Dollard state, which is not this state, this is just the eigenstate of free Hamiltonian, right? But the point is that the fact that the trajectory is not a free trajectory, we should not look at free Hamiltonian. We should look at that Hamiltonian whose trajectory is this one. And then it turns out that this state is precisely something like e to the, I'm writing it a bit schematically, minus I alpha divided by mod p. This is not very, I'm not being very precise. Some e to the minus I alpha by mod p, I'm being very schematic, times log of epsilon, something like that. So times the free state. So yeah.
T is not so important, but T is not dimensionless. So you should write T by T not.
Thank you. So what Sachin is saying, and actually this is going to be part of the problem that we discuss, that this doesn't make any sense because log argument cannot be dimensionless. So when I'm saying t going to plus infinity or minus infinity, I simply mean t larger than some fixed time. So we can take some reference time t naught, and then this makes sense. Okay, so that is what we mean by when t becomes t by t naught goes to plus or minus infinity, then this is the trajectory. This and then it was, so the idea was that these states are the problem. So we got a wrong answer because we use wrong states. We should not use the states we usually use in quantum mechanics, but we have to use these more complicated states. Yeah. No, this comes out of our calculation because of the fact that you see that if at late time, you see that at late time we can start here. So you see that if I substitute this in the denominator, then you will get at large t, you just get t square here. So you want the second derivative to go as t square. That must be a log then.
C has a dimension of time.
C is exactly. C is some, exactly. C is because this thing is coming from some acceleration term. So yeah, right, absolutely. Yeah, there is some time scale there. Yeah, I mean, so it could come from some mass of the particle, charge, etc. Yeah, you are right, absolutely correct. So all of them have same dimension. I mean, it's interesting also that although I have not explained it, that you will always get this term vectorially, it's proportional to v. Like it's not some other vector. So it's okay. This is for q by r. Yeah, exactly, because that's the equation, right, for q by r. So usually we don't, deal with it in quantum mechanics because of this problem. So there we will not have a problem. So I think usually in books, when they do scattering theory with spherically symmetric potentials, they start with at least r square. Is not there, yeah, because if this became cube, then this will become 1 by t actually. So then there is no, then the at late time trajectory is still free. Yeah. Okay. So this was a solution for non-relativistic scattering problem with Coulomb potential, and now we want to understand what is the solution when we go to the theory that Indu explained, which is quantum electrodynamics. But before that, I will stop and ask for students if there are any questions. Okay. Please stop me, okay, at any time. And let me go to the thing that we want to do now. So now that we understand this implication of zero S matrix, we want to see. So of course, whatever happens in non-relativistic quantum mechanics, there should be some implication of that even in relativistic quantum mechanics, because non-relativistic quantum mechanics is a special case of relativistic quantum mechanics. So it's not going to happen that this problem suddenly disappears if we do quantum field theory or relativistic quantum mechanics. So let me first, although Indu did already did an introduction, let me give a very small, quick introduction of what we will need for quantum field theory. We will not need much. So just a very quick review of what we require of quantum field theory. So we are going to look at a very specific theory. It's a theory where we have particles. So I'm first writing some words, then we will put some equation. So we have particles with charge but no spin. So these kind of particles are excitations of what we call scalar field that Indu also explained. So we have particles with charge. If you have particles with charge, then even, of course you could imagine that they interact with each other via electromagnetic interaction, right? Which means that obviously this would imply we have electromagnetic field. And the theory we want to study is interaction of such particles with electromagnetic field. Okay, that's our interest. So this is the theory, and this is the theory that, of course, you are very familiar with from your Jackson. So it's just it's classical electrodynamics, and its quantum version is what we call scalar QED. So scalar is because these particles have no spin. So everything I'm saying today, it's all true even if you had, as Indu did in her talk, with normal electrons or fermions. But for what we want to discuss, it's not important. So it simplifies our life. For her, being scalars complicated her life, but for us, scalar will simplify our life. I mean, just for the purpose of this discussion. So, so now the point is that, so we want to understand scalar QED, but we don't need much. All we need is the following. So the key object we need is the following. That suppose you have a particle which is very similar to the diagram I drew before with momentum P, but now we have a relativistic particle. So I have to have a 4 momentum. I'm assuming all of you are familiar with 4 momentum. So 4 momentum is simply a momentum whose zeroth so it has a time component, which is just the energy, and it has a space component, which is a 3 vector. So have you guys seen this? Okay, so this is a vector in Minkowski space whose time component is this and space component is just P. And you can check that if you do, if you look at, so if you do this, then you simply get m square, where eta is just a -111 line element of the special theory. So I hope you guys have at least seen it in some form. So okay, so we have some particle with some initial momentum. So initial I will write like this, and just to be explicit, I will put a mu here, so we know it's a 4 vector. And then we want to see how it interacts with a electromagnetic field. And only thing we are going to assume is the excitation of electromagnetic field is a photon. Okay, so photon we are going to represent as a wiggly line. So I have a photon, and photon we all know is completely, even from our classical electrodynamics, right, is completely characterized by its momentum. So every momentum is 4 momentum. So we'll write as k mu, and its polarization. So let's call it epsilon. Okay, so that's the data we need for a photon. And so I have a particle coming in, it can emit or absorb some photon, and it can, so its momentum will change, and you get the particle with momentum Pf mu. Of course, the charge of the particle will not change, right? Because photon doesn't carry any charge. So whatever charge this particle had, this particle has same charge. So if I say that this particle has charge Q, electric charge Q, then this particle also has charge q. Okay, and these are same.
And maybe you can mention that this epsilon has nothing to do with the cutoff epsilon.
Oh, yeah, sorry. This epsilon is the polarization vector. So this epsilon, you should also think of it as a 4 vector which satisfies epsilon mu k mu equal to 0. It has nothing to do with any cutoff. It basically tells us whether our photon is circularly polarized or elliptically polarized or whatever. So this you must have seen in some form, right? The epsilons. Like typically maybe in Jackson and all, they look at this. You may have seen it as a vector, spatial vector, but that is simply because you can always choose a condition on epsilon mu such that epsilon 0 is 0. So you can choose different condition for epsilon, but you have to choose only one condition. And so typically in classical mechanics, I mean electrodynamics, maybe they use this condition, but you don't have to. You can also use this condition. Okay. And now you can ask, okay, so QFT, what QFT does is tells us what is the probability of this process happening, and actually it's very easy to write down. So the probability for this particular process to happen is simply given by the charge times the difference in the momentum, which is a 4 vector, times epsilon mu. Okay, that's all it is. So this is some data that from QFT. Actually, we don't even need quantum field theory, just the combination of quantum mechanics and special theory in fact tells us that this has to be the coupling between a charged particle with no spin and photon. Okay, so this is what this I want you to keep in mind, which is this thing here. And now if you want to study a process, so we can study many processes. So let me give an example. So consider the following scattering process. So by scattering process means particle come collide and go out. So consider the following scattering process. So it's a reaction which is that, let's say that you have 2 photons. So I will always denote photon as gamma. So I can have 2 photons coming in, they can collide. And so in quantum field theory, everything that you can build out of such diagrams is allowed. That's the thing of quantum field theory, because you can have yeah. So special theory basically tells you that you can start with say 2 particles or 1 particle, and it can decay into 2 particles, etc. So so whatever you can do out of these 2 photons is allowed. But the most simple thing you can do is they could collide and produce for you one particle P1 with a positive charge. Let's call it plus Q, and scalar particle P2 with a negative charge. So just to write it in more detail, I can have 2 photons with some momentum K1, polarization epsilon 1, and polarization epsilon 2, momentum K2. They can collide and they can do something very, very complicated. We will see in a minute what these complicated things are. And they can, final product of this collision is 2 charged particles with equal and opposite charges. So this P1 plus Q and plus P2 minus. Okay. And now we want to understand what is exactly what we did in non-relativistic quantum mechanics. The question we are asking is, what is the probability amplitude for this process to occur? And now in quantum field theory, 2 bad things happen, which as actually Indu explained, combined to save us in some sense. But let me first just quickly recall what happened. So 2 things go wrong, unlike in the non-relativistic case where only one thing went wrong, which was this fact that the states were not states of free Hamiltonian. So let me first schematically tell you what two bad things can happen. So let me first draw this diagram for this process. So the simplest diagram you can draw, which you can build out of this one, which you have to stare at it a little bit, is the following. So I will explain why this diagram is built out of that diagram. So you have 2 photons, one with momentum K1, polarization epsilon 1 and epsilon 2 K2. And so this photon comes, it can split into two particles, and this particle can come and it can split into a photon and or this particle can come, it can combine to a photon and give another particle. So if you stare at it a little bit, this is really a fusion of these two diagrams. So this diagram is literally this quantity here, this diagram here, and it's same as this one. And the only thing that is new here, which I have not explained, is the fact that there is a scalar particle which sort of didn't live forever. So it started here and it ended here. So this diagram is called Feynman diagram, and this is something that is allowed in quantum field theory. So it's something that is telling you that you have a photon came, it decayed into a particle and another particle, but this particle somehow didn't want to live long enough, so it collided with a photon and gave us another particle. Okay, this is called Compton scattering. This process is called Compton scattering. Or actually, no, not really. No, sorry, that's a bit. That's a cross process. Yeah. Okay. So this is our setup. Okay, this is our setup, and now there are two reasons this amplitude vanishes. I mean, goes to zero. And one reason is the following: that if I give you this process as opposed to this process, so this is what we are interested in because that's what this is. But suppose I gave you another process, which is this, except that this scalar itself also emitted a photon. So this is something you should just remember, that in quantum field theory, whatever it can produce will get produced. So that's a slogan of quantum field theory. Whatever is allowed is going to be produced. So for example, you see, once we have this kind of a diagram allowed, then this scalar could always produce a photon and also another scalar. So everything that is allowed is produced. Okay, that's the motto of quantum field theory. Okay, so let's do it like that. So we have this, and then we have some P1, P2, and some photon with, say, some momentum K. Okay. But now the point is that photon momentum can be as small as we want, right? Because photon is photon can have a so this K is a 4 vector, and this 4 vector, because photon is massless. So if its 3 vector is K, then its energy is mod K. So how many of you are familiar with this notation, that the given electromagnetic wave with wave vector K, the corresponding energy of the photon is this? Have you guys seen this? Yes. So, but you see, contrast this with what happened for the massive particle, where it was square root P square plus M square P. So no matter how small P is, the energy of this particle is always M, right? Because even if P is 0, the energy is M. It's the rest mass energy. But of course, we know photon's rest mass energy is 0. So so we can so K mu or mod K can indeed go to 0, is allowed, which is basically telling you that you have a photon with very large wavelength. But if K is very, very small, which means that okay, so I should say one more thing. Say that again. Yeah, it's K. I mean, I'm just drawing it as K. Yeah, I was about to write that. No, I'm about to write that now. So the one thing which is different in quantum field theory, which is easier about quantum field theory as compared to quantum mechanics, is that in quantum mechanics, if you remember, you may not have total momentum conservation. So if your potential breaks translation invariance, then momentum is not conserved. But in quantum field theory, because we are in the domain of special theory of relativity, momentum is always conserved because there is space-time translation symmetry. Is this? Have you guys are you familiar with this? That if such a process, total momentum is always conserved. So K1 plus K2 is equal to P1 plus P2. Now, as TRG said, that if this is already true, then how can I emit another photon? But it is indeed true that because K can be as small as it wants, I can have a process where K1 plus K2 is approximately equal to P1 plus P2, in the sense that K1 plus K2 is P1 plus P2 plus K, where K is a very, very tiny photon momentum. So that means that if in fact K can also go to 0. So that means that for every incoming momentum K1 plus K2, I could emit my scalar particles and as many number of photons as I want, in the sense that I'm going to now make a statement which is going to be key for us, which is the following, that let us say that P1 plus P2 minus K1 plus K2 is a very, very small 4 vector. See, epsilon is a 4 vector, but it's very small. It's like magnitude is very small. But now we can ask, okay, that means that the number of Ks I can emit should be, suppose I emitted n such photons, okay, K1, K2, K3, like blah, blah, blah. Then, of course, because the missing momentum is epsilon, whatever number of photons I emit should satisfy this equation. Right? Is it clear? Because the total momentum of whatever photons I am emitting should be equal to the missing momentum in my process. But the fact that each k can be as small as you want, that means this n can be as large as you want. Is this point clear? So because any k, because mod ki can go to 0, which implies n can go to infinity. Okay? But we know this is a basic thing of quantum mechanics or quantum field theory, that the total probability when you sum over all possible states is always 1. But there is no way that the total probability is 1 when you can have infinitely many particles, which means for every process, if one photon is, so the total, you can emit 1 photon, 2 photon, infinitely many photons. But that means for every process, probability has to be 0, right? Because if it was not 0, then it cannot be that for infinitely many possibilities the sum gives us 1, right? So this implies that the S matrix of QED, the scattering amplitude of QED, this quantity. So let me first put some notation. So we are always going to write the transition amplitude like this. So I will not write the polarization vector for photon, because whenever I use K label, it means it's a photon. If I use P, it means it's this particle with charge. So this probability goes to 0. It goes to 0 because if it didn't go to 0, there is no way total probability will add up to 1. So this problem is called infrared catastrophe. So you may think, well, this problem is slightly different than the problem in the non-relativistic quantum mechanics, where the problem came from pictorially from this kind of a process, right? Sorry. So the problem came not because where these are like pictorially representing Coulomb potential. So here the problem came because Coulomb potential is doing something drastic, whereas here it looks like the problem is coming because we can emit any number of photons. But it turns out that this process also has this problem. So there are two problems. So this is one problem. Second problem is basically what we saw in the non-relativistic case, and that I will go a little quickly. So there's a double issue in quantum field theory as opposed to quantum mechanics. By the way, just as a nomenclature, this is called real infrared infrared problem. Real infrared problem. Real because it's caused by real photons which are coming out. On the other hand, I can look at a diagram very spiritually similar to this, but in our case, in the case of relativistic quantum mechanics, and that's simply this diagram. So you see, you can look at a diagram like this because, as we are discussing, anything that can be produced will be produced. So you can have a diagram where a photon comes out from here, but it's not very long-lived, and it gets terminated here. Okay. So anything that you can draw is always allowed. And so here you see that this, now it turns out that this particular transition, if you compute this, so this is a bit hard to compute, but I just give you the answer. So again, let me write the momenta. And you can ask, okay, what is the transition amplitude for this process? So this process is not quite same as this process, because I am having this extra short-lived photon which came out and got absorbed here. And I will not give you the detail, but whatever this turns out to be equal to whatever is the transition amplitude for that thing times the following integral. Okay, so I'm now writing some integral. It comes from some rules of quantum field theory, but don't worry about it. But just so that you can see the expressions, it is an integral over some 4-dimensional space. So this dot is just a 4-vector dot. I really hope you are okay with this. So this is the integral from all over all 4 momenta L. So I just write it as 0 to infinity. And you see here that if you look at the integration at the lower limit 0, then you see this integral looks like literally looks like integral dx by x. I mean, dx by x, dy by y, because there are 4 powers of L in the numerator and 4 powers in the denominator. So there are like so it's so it looks like it's an analog of this integral dx by x, because it has equal number of powers in a numerator and denominator, and this integral at lower limit goes as a log, right? We just saw it goes as some log of epsilon. We have to regulate it. So same thing happens here. Sorry, I cannot do justice to this, but when you compute this integral, it gives an answer which is again divergent at lower limit. So this integral at 0 diverges logarithmically, and so we have to regulate it. Logarithm. So that means that we cannot really write this transition amplitude. All we can do is write, so let me again call this a k1 plus k2 going to p1 plus p2, but I'm going to put a superscript here 1, which basically tells me that one photon was short-lived photon here. Okay, that's my notation of this 1. But now we see that this is actually, this function is divergent. It's not well defined. So only it's well defined if I put some extra epsilon here, which is this epsilon here. But what we want to compute is epsilon going to 0 limit of this, right? Because epsilon is just something I'm putting for convenience, because I don't know what to do when I actually do my integral. But that's the status of the transition amplitude for this process in QED. It has 2 problems. These type of terms diverge logarithmically. On top of that, the total probability will always, if the total probability is 1, which is always true, then probability for any particular process is always 0, because of the fact that you can emit real photons with as much less energy as you want. Okay. Yeah.
If the amplitude going to 0 and calling it the real infrared problem. But why is that a problem? Can't we just assume that, okay, maybe we can't emit infrared particles, and that's why the probability is...
That's an excellent point. So you can ask, okay, why is it a problem? And for a long time, people actually thought this is not a problem, which I am just coming to. So you are absolutely correct that it's not necessarily a problem, but it's not a problem because of what I will discuss now. So yeah. So any questions so far?
Essentially by ruling out photons, right? Because Q by R is just a static potential and there are no photons in the theory, so you just don't have this solved.
So the usual non-relativistic quantum mechanics don't have the real infrared problem.
Yeah.
But the relativistic has that, but also has the Coulomb analog problem, which is...
I'm saying that in the non-relativistic case, the reason it is not there, I guess, is because of the fact that the potential is Q by R and there are no photons.
There are no photons. Q by R problem is there, and that was resolved because resolved in the sense we understood what our mistake was. Exactly, it's related to this. Yes. But I'm saying there we've identified our mistake, that the states we used to define scattering theory were wrong states. Okay, that just came out of looking at the trajectory of a classical particle, right? So here clearly we have some intuition that this problem, as we will discuss, could be resolved by something exactly analogous. But we also have to see what happens to this other problem. But before that, let me answer. Yeah, sorry.
No, go ahead.
Yeah. So let me first answer means in agreement with him. So in some sense, one could say that this is not a problem because transition amplitudes are not physical observables, right? It depends on what we compute physically. So let's try to see what we compute physically in a let's say when we do LHC or when we look at colliders, and what we compute physically are So this is just a name, but I will explain what this means. What are called, so I will explain in a minute what this means. Semi-inclusive cross sections. And what this object is the following, and it's not very hard to understand. So because it's, you can also see it's related to really what you would measure in a lab. So let's look at the same process. So you have two photons, and they went into two charge scalars. But in general, of course, any such process will emit some photons, right? So let's say X number of photons were emitted. But let us say that we are interested in asking a question: what is the probability of the two photons decaying into two scalars? And so we are not interested in measuring this radiation which is going out. This is some noise for us. So how will we compute it? The way we compute this is we take the transition amplitude for this full process. So let's say A4 plus. So this whenever I write this subscript, I always write the total number of particles in the process. So mod X is the number of photons which is going out. So I compute this where your gamma plus gamma goes to P1 plus P2 plus X. This is my transition amplitude or probability amplitude. So compute probability, I have to square it, and then I have to sum over all possible X configuration, right? And what is what is this photons? The only information we have about the photon is that it has a momentum which is the missing momentum, in the sense K1 plus K2 minus P1 plus P2 is the momentum in the photon, right? So now, so that means that you can have infinite number of photons. You can have one photon, two photon, infinite number of photons, as long as the total momentum is fixed by this constraint. So that's the only thing here, that so Px, you have to sum over all possible photons with only the condition that Px is fixed, K1 plus K2 minus P1 minus P2. Okay, so this is the actual observable that you could expect that we would measure, and this as I will explain, it actually has no such problem. It is finite, which answers your question. So this quantity is infrared finite. I will explain in a minute why it is. Even though this quantity is divergent, as we saw, this particular object that I actually measure in a lab is infrared finite. It has no such divergence problem. Okay, so this is one example of what we call an infrared safe observable, and in fact, this is a very prototypical example which we actually use in collider physics and in LHC, etc. Let me give you another example of a observable which you will immediately recognize, which has no such infrared problem. So I hope the statement is clear that this quantity we are computing in quantum field theory, quantum mechanics itself has some infinities or zeros, etc. But this is obviously, we know that wave function or transition amplitudes are not physical objects. We have to compute expectation value, or we have to compute cross section. And so here we are, you see the cross section that we compute, which we actually measure, doesn't actually have that problem. I will explain why in a minute, but before that, let me give you another example. Another example is something you will recognize. Suppose we take two particles, relativistic, classical. So consider classical physics. And consider the following process. You have two particles, relativistic particles with momenta P1 and P2. They are charged. So let's say they have some charge Q1 and Q2. And let's say that they are separated by some impact, some distance, which we call impact parameter B. And classically, we can ask, right, what is the, and the interaction is electromagnetic. So the interaction between them is electromagnetic. Of course, they also have gravitational interaction because they have energy, but we ignore it. We are simply doing classical electrodynamics. So now we can ask, okay, what is the linear impulse of the first particle? So we can ask, what is final momentum of the first particle minus initial momentum of the same particle? So initial momentum I'm calling E1. So this is what we call linear impulse, right? And this is something we can compute in classical theory, right? You would have done it using, or no, it's really just looking at the trajectory of the particle. So this particle in the electromagnetic field of this particle. So you have to look at the trajectory and compute final momentum, right? At least you can see in principle you can do it. So of course, we know in classical theory this is something we compute all the time. It has no problem like divergence or infinity or anything. right? So you can ask, well, can I compute this object from quantum field theory? And actually the answer is yes, and the answer is simply the following. If you look at the classical, we know that any classical particle is basically a wave packet in quantum mechanics. How many of you are familiar with that? You can, classical physics is limit of quantum mechanics. And the first way we see it is like a point particle in classical theory is like a wave packet in quantum mechanics. So let's start with some wave packets, P1, P2. And ask the following question. So this is my wave packet, okay. And I ask the following question. What is the expectation value of the momentum operator for particle 1? Let's say I'm in Heisenberg picture at t equal to plus infinity. So this is something I want to compute. I start with some initial state. It scatters, it evolves. I want to ask what's the momentum of particle 1 at late time. Okay. Now I think you must have seen this, that in Heisenberg picture, this quantity at late time can be written as the evolution of, remember S matrix operator is evolution from minus infinity to infinity. So that is what I'm calling S operator. So this quantity is same as S dagger P1 operator at minus infinity S. Okay. So this is telling us something interesting, that if I computed from my S matrix the following quantity, and I took the classical limit, it's a wave packet, it's a wave packet. Then of course I should just get, if I take this and I subtract from it the initial momentum, which is P1 mu, then that's my classical linear impulse. And this we can do using our Jackson or whatever, and we know this has no divergence or anything. So that means that, you see, there is another measurable quantity you can compute also out of S matrix, which is finite, which is a specific quantity. I have taken P, but you can take any angular momentum or any other operator, right? So you see that S matrix itself has a problem, but you can clearly compute many things out of S matrix which do not have a problem. Okay. So one thing you could say that, well, then I will close my eyes and say that, okay, and this is what people did for, and I think still do, is to say that, well, S matrix itself doesn't exist in the sense it's divergent, but all the observables I actually measure exist and they have no problem. But thanks to the Dollard's work, there is still an interesting question to ask, right? That is there a good S matrix, right? So now we are, is that answering your question? Okay, so now we will, how much time I have, Rakesh? 20 minutes? Okay, so maybe I go a little, maybe I stop here and see if students have any question. Otherwise, I can go a little slightly more technical then. So Rakesh, is that 25 minutes I can take for discussing little more? Okay. So now I will try to at least get time to tell you something that we have been doing with, I erased it. Amit Suttar, who is a student at IMSc, and Ashok Sen, who is at ICTS, in order to understand what is the what are these infrared finite S matrices. So again, if you and I think this is exactly what Indu's talk was all about also, that you can compute observables without really worrying about whether the S matrix itself is finite or not, because as she showed that even when you have far worse IR, in fact divergences like in thermal field theory, in cross sections, I think she did you call it inclusive, or but you computed just inclusive cross section, right? But so she didn't call it this, but she wanted to avoid jargon, but this is the quantity she also computed, but in a much more complicated system. So she had worse problems. But the upshot was the same, that look, I can compute these things without worrying about the S matrix itself. But still, it's an interesting question to ask, and it has actually interesting answers also. Yeah, please. Yeah. I was about to say that now. I will say that now. So let me now say, I think that, say that why these two problems combine and cancel for one of these. So let's go back to the semi-inclusive cross section. So I'm just, I always write SICS as a short form. So semi-inclusive cross section, remember, is this. I just write it X such that Px is. Okay, and now we know that this S matrix has two problems. So pictorially, let me explain to you why the problem goes away. The problem goes away in the following sense, that if so remember, this is like a square of my A, and my A itself diagrammatically look like this. Let's say I'm just drawing one diagram. You can have many, because everything, remember, that can be produced will be produced. We just draw one. And I'm going to, these photons can be emitted from either of these two legs. So I'm not going to bother. So I'm just going to draw X photons like this pictorially. Okay, this is X. So this is schematically, very, very schematically, this is one representative for this particular process. Okay, so you have two photon state came and they created some short-lived particles. They went into two scalar particles with momentum P1, charge Q, P2 minus Q, and bunch of photons, which we are calling X. I hope it's a picture is clear. And now we want to do like a mod square of this. So when you do mod, and then we want to sum over photons. No, because the cancellation will happen between the loop, one loop and the. Yeah, I will just. So yeah, but thank you. No, but thank. So let me. Indu is correct that there is also a simpler diagram that I did not draw, which I should have drawn, which is this one. So this is all part of quantum field theory. You can add more blocks like this. You get many diagrams. But let's look at this square thing. So it has, when I square this, I get following type of diagram. So when I square it, I get a diagram which is. So let me draw one particular diagram. This is my A, where my A4 plus 2. So I am emitting 2 photons. So I am taking X to be 2. That's one, because I am summing over all possible number of photons, right? I am just drawing one diagram to show one cancellation. So I am taking this diagram where X photons are 2 in number, such that the total momentum in these two is equal to the difference of these momenta. And I'm squaring it, and squaring means just drawing it like this. And when I'm summing over the photons, it simply means that I have to sum over, so this photon and this photon, I have to sum over these photons, and that means, so each photon has a momentum, right? This momentum is, let's say, K1, K2. Let's say this is K1 prime, K2 prime. But this mod square is really, I took this and did like mod square of any complex number is Z star of Z, right? So if I call first guy Z, then this guy is just Z star. So that means the case cannot change because it's the same quantity that I'm just doing star on, right? So it just, there are some I sitting here which become minus I in the expression, but the momentum doesn't change. And now when I want to do sum, all I have to do is sum over all the momenta, right, of this. So that means I have to do some integral over phase space of K1 and phase space of K2. Okay, so that's one contribution coming out from here. Now, but of course, because there are many diagrams and I sum them and square them, I get so many diagrams. But let me draw another one, which is the following, which is which was this. Sorry, I'm going a bit fast because I'm out of time. So you can take this diagram and you can, with say 2 photons, and you can draw it here with these 2 diagrams. Okay, and you still have the same sum over the 2 phase spaces. Now there is, so okay, so now if you look at this diagram has a divergence coming from here, which we already discussed. But when you sum over this momenta, this phase space sum, so let me just quickly tell you how it goes. So sorry, I will be a little technical now. So this sum is d cube k1, d cube k2, and then you get some 1 by mod k1, mod k2, and then you get bunch of p1 dot k1, p1 dot k2, p2 dot k1, something like this, p2 dot k2. So you get some divergences here from this diagram. It turns out that this diagram itself has no divergence, but the divergence that comes out is if you had, because the number of x can be 3 also, it can be 2, 3, infinity. So if I look at a diagram which has 3 photons in the first case, so I hope I'm making a mess here. I hope it's clear to the, at least to the more advanced members of the audience. If it's not clear, please ask. So I'm summing over all possible allowed x's. If I take what we call tree level diagram for A4 and look at 3 photons in the x set, or if I look at a 1 loop diagram on one side, tree level on the other side, and 2 photons, you can show that these 2 cancel. These 2 diagrams integral cancel. So this divergence here cancels with the divergence here. The one of the divergences here, and the other thing don't have a divergence. Okay, so it's okay if you don't. It's a bit confusing, but so Indu, is that fine? Yeah. So the issue is that, but one can do it to all orders. So every time you have a divergence coming from the Coulomb interaction, is cancelled with a divergence coming from 1 photon trace. Exactly 1 photon trace, and you can prove it to all orders in perturbation theory that this thing is exactly infrared finite. So the upshot of this analysis is that the cancellation happened because we have 2 divergences. So what saved us was that you have 2 types of divergences. So cross section, it saved you. So in non-relativistic, nothing could have saved you, like, because there is no analog of this what we call real infrared problem. So if Dollard had not given a solution, we would never say that Coulomb potential has any S matrix in quantum mechanics. So there it was inevitable, but in relativistic, actually we can get away because we can compute cross section. And now how much time I have? 15. Okay, so now I'm going to tell you some. But on the other hand, there is a proposal. There has been a proposal for many years, which is inspired by Dollard, to define IR finite S, infrared finite S matrix. So now I would apologize to students because I will go I will take some leaps. And this proposal really, I think, started many years ago by Chung and Keeble. Sachin, was Keeble? And it was culminated in a paper which has become since very famous, Fadhil and Kulish. And let me just tell you what this S matrix is, which is very similar to the Dollard S matrix in quantum mechanics. So the idea is the following: that take any photon state. So let's fix our process. Two photons going to 2 scalars with a equal and opposite charge. Then any photon states remain the same. So if you take a state K1, K2, then keep it same. Why you keep it same? Because photons themselves cannot emit photons and cannot interact via photons also. So photons which are free remain free, so no problem. But with electrons and positrons, they can emit photons and they also can interact via photons. If you give me a 2 electron state, electron positron state, it can have interaction by photons. It can also emit photons. So Kulish-Fadhil analysis was that if you look at asymptotic multi-particle states at late time, again by looking at the Hamiltonian of QED, it is inevitable that the state you find is not the free state, but it has the following form. And now I'm going to write it in a form which is a modern reincarnation of their proposal, which is by Pavel Dush, which is most convenient for, in my opinion, for actual computations. And this is the actual answer for this state. So this is exactly like the Dollard state we wrote, but it's like, it's in relativity. So it has the following form. I will explain the notation in a minute. Okay. Okay, I'll explain. It looks like a bit complicated, but I just. So it has two. This. So the idea is this is not something that you are proposing. By the way, I want to emphasize it's something that you obtain simply by looking at the Hamiltonian of QED and looking at its eigenstates at late times. Okay, that's all you do. So you don't. It's not something that you are just cooking out of thin air. The idea is that the reason your S matrix is ill-defined is because you have made the same mistake you made in Coulomb potential, which is you didn't identify the scattering states correctly. And so in the case of two particles with two momenta, this is the state. So there is some overall phase. Oh, and this eta is completely arbitrary function, which is up to you, typically called profile function, which only should satisfy the property that D4 L mod eta L square is normalized and eta at L equal to 0 should be 1. So it can be any function which satisfies these two properties. It should be normalizable and it should not vanish at L equal to 0. And then this is so for every such eta, I can, this state is, this is the state which is the correct eigenstate of your Hamiltonian of QED at late times. So this is some overall phase, no problem. It depends on the momenta and this function. And then, so you can ask where this is coming from. This is coming from the fact that if you have two particles, they are always interacting by electromagnetic interaction. And that part is really capturing, coming here. And the fact that any charged particle can emit photon of, the particle which is moving slowly and slowly, no matter how slowly it's accelerating, it can always emit some photon. So that emission of photon loop is captured by this one here. And this is some function which is just the probability of emitting a very small energy photon by a particle. So, but you see, this is not a phase because this is actually this is a creation operator for a photon. So this is some complicated operator which basically captures this idea that you have a charged particle, no matter how low its acceleration, it will always emit some photon. So that creation of photon is captured by this thing. Okay. So this is the idea of Coolidge-Faddeev was when you take this and if you compute S matrix, it should be infrared finite. And it turns out that it is indeed infrared finite, except that there is a problem. And the problem is that both these expressions are in fact divergent by themselves. This is divergent and this is divergent. And so actually you cannot define this state. So the only thing you can do is actually regulate it. So you have to again put some regulator epsilon in both these exponentials. Okay. And you will be worried that then what is the point, right? Because I anyway have to regulate my S matrix, but you gain something. And what you gain is the following. So I'll go fast now.
One question.
Yeah.
So in the case of this non-relativistic thing, you basically change the Hamiltonian, right? When we wanted to...
We didn't change the Hamiltonian. We just realized that our identification of scattering asymptotic states was wrong because the interactions never die down.
So, but in effect, so you had to take care of the fact that the log term was there.
Yes, exactly. So, yeah. So in the sense, the Hamiltonian has a term which at late time is not 0, which we naively think is 0. Yeah.
Here, when you say that it is
Sorry, you don't change it.
No, you're not changing anything. It's just
What you do is
yeah.
you realize that you're working with the wrong
Yeah, that's what I
out states.
yeah.
H, stacking theory.
Yeah, that yeah.
Reference. Oh, yeah. Were you talking about reference Hamiltonian?
Yeah, I was just.
Yeah. But ask your question.
I think I understand
Yeah.
what you're saying. So, but I'm just saying that here, for instance, when you say that you're computing the eigenstate of QED at late times, what does that mean?
So what we would usually do, right? So we take our interaction Hamiltonian. I mean, our Hamiltonian in the interaction picture. So you have some free interaction picture field, and so you come, and it's of course a function of time because it's always integral d cube x dot dot dot, right? And typically what we do is we take asymptotically we take this t to infinity. Okay. Now what happens is that if you look at the 3-point coupling, which is really integral d cube x j mu a mu, it has terms of the type that you can have. So this j is coming from the scalar particles. I am just going very fast. So you have terms like b dagger p1, b p2, a photon p3 with delta of p1 plus p2 minus p3, and you get time dependencies in this kind of factors, as you know, like it's in e to the I ep1 minus ep2 plus photon energy, which is, let's say, mod p3 times t. So because there's a b dagger p1 b2 p2, there's a relative sign here. You just evaluate the interaction part of the Hamiltonian. You get a term like this. Yeah, just give me a second. So now you see what is happening is that typically, if this, instead of a photon, I had like say b p3, like a 5 cube theory, then this will be e p3. So no matter how small your momenta is, there is never going to be a cancellation between these three terms. But here what is happening is that if your p becomes very small, then because of the momentum conservation, these two terms cancel. ep1 minus ep2 are 0, right? So this term becomes 1. So this phase becomes 1 at late time. So this term never dies as long as p3 is 0. So that's the correction. So the part of the interaction where your p3 is small continues to survive at late time. So the Hamiltonian is not free Hamiltonian.
So but then how do you say, then are we able to solve it?
Yes, exactly. So now the point is you want to diagonalize this piece plus the free Hamiltonian. That's exactly what Coolidge-Faddeev did.
And the claim is that this is the solution to that.
Yeah, this is the solution modulo the ambiguity that you can put up. Where is the ambiguity? You can ask, where is eta come from? There is no eta here. The eta ambiguity is simply because when I'm saying that at late times, I have to give a reference time. So that there is some t naught such that for t larger than t naught, my Hamiltonian is free Hamiltonian plus this correction term. That t naught ambiguity is kind of captured in momentum space by this profile function.
So is it correct to think of it as some sort of a Bogoliubov transmission type of thing at late time?
No, it's not Bogoliubov. Actually, it totally destroys the. You see, because the point is that if you look at this term, right, there is no single particle state anymore, because you see that pictorially you should. That's why I draw this also. Like pictorially, you should also always think of Coolidge-Faddeev state like this. These are your free states, and now you are basically having a phase term which depends.
Like I'm just concerned about the fact that because the Hamiltonian is not linear, how do we solve it?
No, but you can actually just look at it. Is simple enough that you can solve it in this case.
So it's sort of, you could think of it as an ansatz, you plug into it.
Exactly. Absolutely. Absolutely. Yeah.
People already mentioned that this transition
Yeah, exactly.
that you are making is a transition from the Fock space to an inequal representation of the algebra of the.
I will come to that.
Secondly, two photons do interact because, for example, nonlinear optics or
No, in QED.
so the fact that there are no net charge is zero. That's the important thing. E plus the two charges.
When I say don't interact, I meant photon cannot emit a photon. That's all. That's all I meant by not interacting.
Net charge is what is important.
No. I just meant in perturbative QED we have no vertex where you don't have a 3-point vertex with, unlike a glue, and you don't have such. That's all I meant. 3 photon vertex. Yeah.
You said they don't interact. They do interact.
No. I mean they of course interact in the sense of here they are interacting, but that's I meant it in the context of the fact that you don't have any other diagrams that you want to draw. You can draw. Yeah. Sorry, but yeah, I was not very precise there. Let me just go fast. Rakesh, 5 minutes or gone? Oh, chair, 5. Okay, so Chetan, is that okay? Yeah. I mean, it's because it's only the P3 soft, we can actually execute it, put answers and solve it. This is really like a squeeze state. I mean, you know. Okay. Okay. Yeah, I don't know Bogoliubov, but yeah. Yeah, Bogoliubov, I mean, okay. Squeeze state, yeah. Squeeze state up to this phase. And the phase is also divergent, but both are divergent. So the point is that at this time, the stage itself requires a regularization. It's not a well-defined state. But if you now, you gain something, and what you gain is if you now compute P1, P2, this regulated Coolidge-Faddeev state you take your S matrix operator, but this S matrix operator also has those epsilon divergences. So we have to regulate them. So let me just call it epsilon. We can compute this quantity. And this quantity in limit epsilon going to 0 turns out to be equal to, okay, this is Coolidge-Faddeev, I mean, result, but which is explored by many people later, times a function, which I'm going to call A, which depends on eta at epsilon equal to 0, which depends on the momenta. And I will explain this in a minute, but the main first upshot is this, that you regulate your S matrix, you regulate your state, and you define the amplitude, and it's what? IR finite. So at least it's a proposal for the IR finite S matrix. But now you can ask, how can this possibly be true? Because of what you just said, that this is some squeeze state, right? So if I take my state, naively if I take this state, and then if I apply a photon annihilation operator on it, right? Then if I had no Coolidge-Faddeev stuff, then this is 0, right? Because in a vacuum, there are no photons here. P1, P2 are the scalar particle states. And naively, it seems like when this acts on this state, this is not 0 because of the fact that this has a dagger here in the exponent, right? So it clearly looks like this is a state where we are, so the basis of our analysis is we have some Hilbert space for scalar charged particles and some Hilbert space of photons. But now it looks like it's totally destroyed because of this. And then it's obviously not going to be true that the total momentum, so you see that the photon momentum is not 0 because it has some non-trivial photon momentum. And if the photon momentum is not 0, we don't know if this thing is true anymore. But it turns out that actually it is true because this is related to what Bal said, that these states are in different, okay, I'm now becoming more and more technical, representation of the QFT operators. I will end in 2 minutes. By which I mean that you can define a displaced photon operator, which also we do in squeeze state, which is of the following form. And this when acts on, you can check by algebra, this when acts on this thing is 0. So that means that when you are with Coolidge-Faddeev states, you should not think that your photons are created by your normal photon operators, but always by these kind of displaced things, okay, displaced operators. So with this, so this is a new definition of a photon annihilation operator. Of course, the similar one you can write for the creation operator. Call it this. And now I'll just end that you can now ask the question, okay, why did we do all this? First of all, is it even true that the observables which are well defined with normal S matrix remain, do they give same numbers if you use this S matrix? And if so, what is the form of the observables in this new S matrix? So these are the two questions we can try to understand. Question 1, which is, do semi-inclusive cross section remain invariant under, I will just call it FK transformations. This is not a trivial question, right? Because these are now, as we are seeing, that they are very different type of states. So there is no guarantee that this is true. But in a minute, do I have a minute? Okay. But I will give a quick argument as to why it's true. There is a, in some sense, a more rigorous proof. And the quick argument is the following. That if you consider at this level, this S matrix, then you see that because I'm not, my epsilon is finite. So this state is just some change of basis from my Fock state because epsilon is finite. So I have not done anything more than that. So in that sense, if I work with Coolidge-Faddeev states, so you know what, and I take limit epsilon to 0. If I do this, then I expect this answer to be the same as this answer, obviously, because of the fact that, why? Because of the fact that this itself at this stage, this is a change of basis, and this quantity we know is infrared finite. So because it's infrared finite, the epsilon goes 0 limit cannot be discontinuous. I'm giving a very quick argument as to why we can almost be sure that if I use the Coolidge-Faddeev state and compute these cross sections, our answers won't change. I must say that this is not true for all proposals of Coolidge-Faddeev. There are some proposals where this answer changes by small amounts. Let me write like delta. And one can use this consistency condition to rule out such proposals. We can say that whatever answer we use in collider physics should exactly match. So there are many recent proposals which give this answer up to some correction. So we can, if we use this fact that whatever we measure with normal cross S matrix should be, those numbers should remain the same, then we can rule out those proposals. Now finally in 1 minute, we can ask, can I write, but this is a bit cheating, I'm doing a bit cheating because I'm writing everything first at the regulated level. If I write this at epsilon not 0 and sum over x, already in fact divergence have disappeared. So I have not really done anything with Coolidge-Faddeev in some sense. So we can ask, can I write semi-inclusive cross section in terms of this S matrix? That is, can I take the epsilon go to 0 limit before summing over x? And I'll just write the form and end there. So that is one of our results with Amit and Ashok, that the semi-inclusive cross section has the following form. I won't bore you with all the details. I'll just write the main structure. So this phase space measure over x. Actually, sorry. I'm just going to write some form just to show us that there is a nice result that one can write. Yeah, so sum over x, but first I'm summing over subsets of x, proper subsets of x. Then I'm splitting. So x is my photons I'm summing over. So first I'm summing over some. I'm just writing the final answer. So phase space measure I'm splitting into x minus y and y, and then what I get is some. Okay, I will write it now. Times integral. Okay, sorry. Product over all y photons. 1 minus eta tilde over y photon square times mod a eta epsilon equal to 0 S matrix square. So I will just explain in a minute. I can tell you more. That what happens is that if I work with Coolidge-Faddeev S matrix, the virtual divergences have already cancelled. There are no divergences left. So then you may be worried that the real divergence coming from trace over x, where do they go? And actually they get cancelled by the fact that we are in inequivalent representation of the Hilbert space. So we have to sum over what are called different vacua. And the sum over different vacua actually cancels the real infrared divergence, the x divergence. And that effectively, so the sum over vacua effectively implements itself as a change in the measure factor of the phase space. So you can write this cross section purely in terms of Coolidge-Faddeev S matrix without ever knowing about the regularized S matrix. And okay, I mean the motivations of looking at this consistency comes from some string amplitudes, but we can forget about this. So I end here. Sorry, I went over time, I think.
See right away that this state what is constructing does not carry the representation
Lorentz group, it doesn't, no. Yeah, right.
Is spontaneously broken.
Yes, but that will not stop us computing the semi-inclusive cross section.
Cross-section,
Yeah,
very good cross.
yeah,
Unitary operators don't exist.
yeah. I mean, you're right. Boost is spontaneously broken. That's the inevitable feature of these states.
So what you may
All
know
the
that
measured quantities are Lorentz equation. All the measured quantities obey Lorentz equation.
Yeah, so cross section is fine.
cross-section
So where will you experimentally find the violation?
Um, No, I think, yeah, I mean, I think in principle, I mean, yeah, I mean, you can, I mean, it's not a surprise, right? Because they are addressing charged particles with soft photon states. So local boost cannot exist. Yeah. Yeah.
I would like to find out, I go in your brain and check what is happening in that experiment.
Yeah, I don't know. Bal has thought about this a lot more. Yeah.
it's not an issue. For example, if you take a ferromagnet, in the ferromagnetic case also similar thing happens.
Yeah.
Because there are infinite number of inequivalent representations. But the spin is rotated.
Yes.
But the expectation value of the observables in both these states are the same. And there are Goldstone modes.
Correct.
I mean, they are
Yes.
normally they are unitarily equivalent, but if there is no unitary operator,
Yeah.
they rotate the spins at infinity. So the expectation values of same thing happens, but there is a new prediction. There are Goldstone modes. The Goldstone modes is a consequence of this fact that you have this.
Yeah.
Now the question I am asking is.
No, so that,
what are
sorry,
the
just
Goldstone
to,
modes here?
yeah, it is, yeah, it certainly, I didn't have time, but the point is that the fact that you get the same semi-inclusive cross section comes from the fact that you have to sum over all possible vacua. So that's the important point. Yeah. So you trace over all possible vacua, all the displaced vacua, because when you're tracing over, when you trace over X is photon set, which means you also have to trace over zero frequency photons, which is,
Somehow it is a mixed state.
yeah, it is a mixed state, of course. So I'm just computing this semi-inclusive cross section, but the sum over X is modified now because it also includes some more vacua. No, but I'm saying it's a fact that saves us, that we have an answer which we know is correct, which comes from usual S matrix. I mean, I'm taking that as a starting point, but that answer matches with what we do with Coolidge-Faddeev S matrix, even though we would worry that that cannot happen, because if virtual divergences cancel, how can real divergences, it has nothing to cancel with, but it's cancelling with the fact that you have infinite dimensional space of vacua and you are tracing over them.
Let me go back again. What are the Goldstone modes for spontaneous breakdown and
For the Lorentz group. No, I was talking about the zero frequency photon. So those ones, sorry, yeah, that I don't know. So I don't know, yeah.
Basic question. So
Yeah.
The point that you were making here was that this epsilon P1, P2 states, which had to have a cutoff, but when you compute with this object, it's actually.
Yeah, because both have divergences. Yeah, it's like the Dollard thing, right? Similar to Dollard thing, yeah. So this object itself is IR finite, but that's not enough. I mean, we should check that all the observables come out to be, I mean, we are thinking that the cross sections are a consistency condition, and to see how, how that turns out. And the vacuum transitions are inevitable because they change the phase space measure. Yeah.
Electron plus no photons, electron plus one photon, electron plus two photons. That's how it uses it, right?
No, it's not like that. I mean, Coolidge-Faddeev is, you cannot isolate single particle.
Isolate, but that is the summation of almost assuming a final Coolidge state, right?
No, but if you have two particles, charged particles, you cannot write it as Coolidge-Faddeev over one electron, two. You cannot. No, but yeah, for scattering we need at least, we are looking at two. But anyway, go on. Yeah, sorry. Yeah. Yeah.
Plus one, zero photon, one photon, two photon.
Yeah.
So what do you mean by different representations of the
Yeah, exactly. So if you look at this, if you look at this operator, this depends on the matter momenta. I mean, I was not going into full detail. So this operator is not unitarily equivalent to this operator, because this, although in the photon space, this is an identity operator in the photon Hilbert space, but it depends on the density matrix of, I mean, the density operator of the charged particles. So this is not a unitary equivalent to this state. And so, but of course, in the photon Hilbert space, this is proportional to identity. So if I change a photon to this operator and dagger to its equivalent, then the commutation is still 1 because this commutes with this and it commutes with itself because it's just high identity operator. So these are called displaced photon operators, which are not unitarily equivalent to the original operators. And this it's coherent state. Yeah, but the zero frequency, the fact that you're, yeah, because you're soft photon anyway. Yeah. So, yeah.
This state is a coherent state, as we say. You can obtain by differentiation of electric field multiplied by a test function is given by this.
Yes, yes.
And integrate.
Yes.
But there's a theorem that if and only if that test function is square integrable,
Yeah, that was condition.
is it unitarily equivalent?
Yes, that's a condition I
It's
put.
not the case.
No, that was my condition. I started there. My eta was square integrable.
Then what I think is when only if the coefficient, this object here is square integrable in the appropriate measure, is the state use, the transformation stays in the same Fox space. In this case,
No.
I think it will not.
No, it will not. I'm not. No, I'm not.
No, we are agreeing. So we are going into a new representation.
Absolutely. That I have no doubt. We are in a different representation.
That's a test.
Yes, yes.
So I still do not know what is going to.
No, this I don't know the answer to that question. But yeah, as a limited question we have asked, which had other motivation. But the fact that one question was, where is vacuum transition really playing a role in observables we compute? Actually, they play a very crucial role if we actually compute them. I mean, in my opinion, one problem so far with Coolidge-Faddeev is no one has actually used them to compute the usual perturbative observable. So when we actually compute, we really see power of Coolidge-Faddeev, all the at least some of the subtleties. The one that you mentioned about the vacuum, the inequivalent representation. About the Goldstone, I don't know. Maybe some other observables where Goldstone may matter. Goldstone for the Lorentz may matter, but I don't know right now. Yeah.